Hey everyone, and welcome to this deep dive into neural networks.
How they learn, how we train them.
Yeah, exactly.
Oh,
So you're curious about all the learning that's going on with these powerful tools, right? And we're going to try to break it down.
we are.
And we're going to be looking at excerpts from the deep learning textbook.
Great book.
Yeah, a very dense book, but a very good one.
It is dense.
I think it's interesting how much buzz there is around deep learning right now.
Yeah,
But the concept has been around for quite a while.
it has. It's been around since the 1940s.
Wow.
Yeah. So it's gone through.
That's a long time.
It's gone through a number of rebrandings.
Really?
Yeah.
Wow.
It used to be called cybernetics and connectionism.
Oh, wow.
Now it's deep learning.
Okay.
But the kind of underlying.
So it's not a brand new concept.
No, it's not.
Okay.
But the current focus is on supervised learning
Right.
using massive data sets.
Yeah. And so that's leading to a lot of breakthroughs.
It is.
That's interesting.
Yeah.
So before we jump into the actual training process, though,
Okay.
maybe we should take a step back and just think about neural networks in general.
Yeah.
Like, what are they in essence?
They're sophisticated function approximation machines.
Okay, so
Yeah.
function approximation machines. Can you maybe explain that in simpler terms?
Sure, they learn the relationship
Yeah.
between inputs and outputs.
Okay.
So you have a bunch of data points, and a neural network can kind of suss out or figure out the underlying function that connects those points, even if it's a very complex and nonlinear relationship.
Okay.
Yeah.
So it's all about creating a network that can predict
Yes,
outputs based on inputs.
exactly. And it can generalize.
Okay.
So it's called statistical generalization.
Okay.
It's like teaching it to understand the underlying patterns in the data,
Yeah.
not just memorize examples.
So not just memorization.
Yeah,
But
the
actually.
generalization.
Yeah. Getting those patterns.
Yeah.
Okay, that makes sense.
Yeah.
So how does this learning process actually happen though? Like where does it all begin?
So it all starts with forward propagation.
Okay.
It's like imagine data flowing through the network, like a signal,
Okay.
traveling through layers of neurons.
Oh, okay. So it's like a chain reaction almost.
Yeah, exactly. And each layer transforms that data a little bit,
Okay.
extracting features and patterns.
So you start with some input and it goes through this chain reaction
Right.
and then ends up with some output or a prediction.
Exactly.
But how does it know how well it's doing? Like it needs feedback, right?
It does need feedback. That's where loss functions come in.
Loss functions.
Yes.
Okay.
They measure how far off the network's predictions are from the actual values.
Oh, okay. So it's kind of like a scorekeeper almost.
Exactly. Yeah, like a scorekeeper telling it how well it's doing.
Okay.
And we want to minimize that loss.
Right.
So we want to make those predictions as accurate as possible.
Okay.
To do that, we use optimization algorithms.
Optimization algorithms.
Mm.
So what do those do?
They're basically the tools that fine-tune the network's parameters to get it to make better predictions.
Got it.
One really popular one is gradient descent.
Gradient descent. Okay.
Yeah.
So that adjusts the parameters to make the predictions better.
It nudges them closer to the targets.
Okay. So I'm starting to see the bigger picture here, but how does it know which parameters to adjust and by how much?
That is where the magic of backpropagation comes in.
Backpropagation. Okay.
Yeah.
This is where it gets really interesting.
It does. It's like imagine a detective
Okay.
working backwards through the network,
Okay.
tracing the error all the way back to each parameter
Okay.
and figuring out how much each one contributed to that final mistake.
So it's like a deep analysis
Exactly.
of where things went wrong.
Exactly. It's like assigning blame to different parameters.
Okay.
And backpropagation tells us which ones need to be tweaked and by how much.
Okay. So backpropagation is giving these optimization algorithms
Clues.
that it needs to make smart adjustments.
Yeah.
Kind of like a feedback loop.
Exactly.
Okay, this is fascinating.
It is.
So all this sounds very straightforward, but I've heard that there are actually some challenges in training these neural networks.
There are.
So what are some of those?
So sometimes we run into things like the vanishing gradient problem.
Vanishing gradient problem.
Yeah.
What is that?
So the gradients are basically telling us how to adjust the parameters.
Right.
And sometimes they get really, really small
Okay.
as they propagate back through the network.
So it's like a signal fading away.
Exactly.
Oh.
As it travels a long distance.
And so that makes it harder for the network to learn.
Exactly. Especially in those early layers that are far away from the output.
So they're not getting the information they need.
Right. They're not getting those clear signals on how to adjust their weights to help the network learn.
Wow. And what causes these gradients to vanish?
So it can happen in really deep networks with many, many layers, or sometimes when you're using certain activation functions that compress those gradients.
Okay, so the depth of the network and the type of activation function you're using can impact this.
It can.
Okay.
And then on the flip side,
Yeah.
we have the exploding gradient problem.
Exploding gradients. So that sounds a bit more alarming.
It is, so instead of vanishing, they get really big,
Okay.
which leads to instability during training.
Oh, okay.
Yeah, the network's parameters can kind of swing wildly and make it hard to find a good solution.
So vanishing gradients is like hitting a wall, and exploding gradients is like losing control of the steering wheel.
Great analogy.
Okay.
Yeah, both of these things can cause a lot of headaches during training.
Got it.
And they are often linked to this problem of proper initialization.
Initialization.
Yeah,
You mean how we set up the initial values of the parameters?
exactly. So
Okay.
if those initial weights and biases aren't set appropriately, it can trigger vanishing gradients, exploding gradients, or it can even lead to the network just getting stuck at a bad solution.
Oh, wow.
Yeah.
So choosing the right starting point is
Yeah.
crucial.
It is. It's like setting off on a journey, you know? You
Mhm.
want to make sure you're heading in the right direction from the beginning.
Okay.
Yeah. There are various initialization strategies that are designed to kind of address these issues.
Okay.
Yeah. And promote stable and efficient learning.
So there's a science to this initialization.
There is.
It's not just randomly assigning values.
It's not.
Okay.
Well,
Wow, this is really shedding light on all the complexities of training neural networks.
it is. And we've just scratched the surface.
Really?
Yeah. There's so much more to explore.
Oh, wow.
Like, we can talk about specialized architectures and advanced techniques like regularization.
Regularization. Okay, what's that about?
So regularization techniques are tools to prevent overfitting.
Overfitting.
Yeah. Overfitting is when a network kind of gets too enthusiastic about the training data and starts memorizing it instead of generalizing.
Oh, so it's like a student who just crams for a test,
Exactly.
but then can't apply the concepts in the real world.
Yeah, exactly.
Okay.
And regularization helps the network find the right balance
Okay.
between fitting the training data well, but also learning those underlying patterns that are going to generalize to new situations.
This is fascinating.
It is.
So it sounds like training neural networks is this very delicate balance
It is.
of a lot of different factors.
It is.
Wow. Okay, we've covered a lot of ground already.
We have.
But this is so interesting. So let's pause here for a moment. We'll come back and continue this deep dive into the world of neural network training.
Sounds good.
All right, we are back, and we are talking about all things neural network training,
Yes, we are.
and specifically these regularization techniques,
Right.
these tools that prevent our networks from going rogue and memorizing the training data.
Yeah, overfitting. That's what we call it.
Overfitting, yeah.
Yeah.
So tell me more about these techniques.
Sure. So one common technique is weight decay.
Weight decay. Okay.
It's like a penalty on large weights in the network.
A penalty on large weights.
Yeah.
Why would we penalize them?
Well, so it encourages the network to kind of keep its weights small,
Okay.
and smaller weights tend to lead to smoother, more generalized predictions.
Okay.
So it's kind of like a nudge towards simplicity.
Okay, so don't overcomplicate things.
Exactly.
Just keep it simple.
Keep it simple and you'll generalize better.
Got it.
Yeah. And then another powerful technique is called dropout.
Drop out.
Yeah.
Does that mean we just drop out of school and stop training?
No, not quite.
Okay.
But the name is kind of fitting.
Okay.
So during training, dropout randomly deactivates some of the neurons in the network.
Wait, we intentionally turn off some of the neurons.
We do.
Why would we do that?
It sounds strange, but it's really effective
Okay.
at preventing overfitting.
Okay.
So it's kind of like forcing the network to learn multiple ways to solve the problem.
Oh, okay.
Because it's constantly adapting to different subsets of active neurons.
So it's like everyone on a team needs to be able to pick up the slack if someone's out sick.
Exactly.
Makes them more adaptable.
It makes the network more robust
Okay.
and less reliant on any single neuron, and it improves generalization.
I see. So these regularization techniques are very interesting.
Yeah,
They really help fine-tune the learning process.
they do.
Is there anything else?
Well, there's also early stopping.
Early stopping.
Yeah.
So this is where we do actually stop training early.
We do, but we do it strategically.
Okay, strategic.
Yeah. So
So we monitor the network's performance on a separate validation set.
validation set.
Yeah, it's a portion of the data that we set aside specifically for evaluating how the network's doing during training.
Okay.
So we don't use it to actually train the network.
So it's like a test run.
Yeah, exactly.
Oh, okay.
And so with early stopping, we stop training when the performance on this validation set starts to plateau or decline.
So it's like recognizing that, okay, you've learned enough now, let's stop here before you start overfitting.
Exactly.
And it ensures that it's generalizing better to those new unseen examples.
Okay, so these are all great techniques to ensure that our networks are, well-behaved
Yeah.
and making accurate predictions.
Yeah.
Are there any other clever tricks that come into play here?
So there's something called parameter sharing.
Parameter sharing. Right.
Yeah, what is that?
So imagine a convolutional neural network,
Okay.
which is often used for image recognition.
Right.
So instead of each neuron having its own unique set of weights,
Okay.
we use the same set of weights across different spatial locations of the input image.
So it's like a detective using the same magnifying glass
Great analogy.
to look at different parts of the crime scene.
Exactly.
Okay.
So this shared set of weights
Yeah.
basically acts as a feature detector
Okay.
that scans the image for those specific patterns regardless of where they appear.
That's really efficient.
It dramatically reduces the number of parameters that the network needs to learn.
Okay.
So it's much more efficient and less prone to overfitting.
Wow. And does this parameter sharing have any other benefits? It does. It leads to something called equivariance.
Equivariance.
Yeah.
Okay.
So simply put, it means that if the input shifts, the output shifts in the same way.
Okay.
So for example, if a cat in an image moves to the right,
Right.
our network will still recognize it as a cat, just in a slightly different position.
That makes sense.
Yeah,
So the network is not thrown off by just these minor changes in position.
exactly.
It's like recognizing a friend even if they've changed their hairstyle.
Exactly.
Aye.
And so this property allows it to generalize really well to those new inputs, even if they differ slightly from the training example.
This is really cool. Parameter sharing is really a game changer.
It is.
So what else is out there?
So another important concept is pooling.
Pooling like swimming pools?
Not quite,
Okay.
but it does involve a kind of reduction.
Okay.
It's a downsampling operation that reduces the spatial dimensions of the data.
Downsampling.
Yeah.
So like making a giant image smaller.
Exactly.
Right.
And one common type of pooling is max pooling,
Max pooling. Okay.
where we take the maximum value within a small region of the input.
Okay.
So imagine you're looking at a patch of pixels.
Okay.
Max pooling would just pick the brightest pixel in that patch.
Okay. So we're throwaway information.
We are, but discarding some information can actually be beneficial.
Really? How so?
It helps the network focus on the most salient features, and it makes it less sensitive to those minor variations in the input.
So it's like highlighting the key points in an article
Exactly.
instead of reading every single word.
Exactly. And pooling also helps with something called translation invariance.
Translation invariance.
Yeah.
Okay, break that down for me.
It means that the network's performance isn't affected by where a feature is in the input.
Okay.
So if a feature moves a little bit, pooling can still capture its presence
Okay.
because it's looking for that maximum value in a region, not its exact location.
Okay. So it's like, I don't care where you are as long as you're somewhere in the neighborhood.
Exactly.
Okay.
Which again is essential for good generalization.
And are there other types of pooling?
Yes. So
Like-
there's also average pooling where we just take the average value.
So max pooling is like finding the tallest person in a room.
Yeah.
And average pooling is like getting the average height.
Yeah. Great analogy.
Okay.
And the choice of pooling method really depends on the task and what kind of information you're trying to preserve.
I see. Okay. Well, this is all very fascinating.
Yeah.
So we've gone through these regularization techniques, parameter sharing, pooling. What else is there?
So let's move on to some specialized neural network architectures.
Specialized architectures.
Yeah. They are designed for specific tasks.
Like what?
So like recurrent neural networks, or RNNs, are designed for sequential data like language or music.
We touched upon RNNs earlier when we were talking about some of the challenges in training.
Yeah.
What is it about them that makes them so good at handling sequential data?
Yeah.
Okay, RNNs, bring them on. Remind me what makes them so special for this sequential data.
So unlike feed-forward networks where data flows in one direction, RNNs have these loops. Okay.
That allow information to persist over time.
So it's like they have memory.
They do.
Okay.
They can remember things they've seen before.
Okay, so for tasks like machine translation or natural language processing,
Exactly.
where the order of the words matters,
The order matters a lot. Yeah.
RNNs are a good choice.
They're a great choice.
Okay. But we did talk about the challenges in training these RNNs.
We did.
Is there anything that helps with that?
So you're remembering vanishing gradients.
Yeah.
And you're right, that can be a major problem with RNNs.
Okay.
But that's where gated architectures come in.
Gated architectures.
Yes. They're
Yeah.
designed to kind of combat that vanishing gradient problem.
So we're building a fortress around our network now.
Well, it's more like we're adding these strategic checkpoints
Okay.
within the network.
Okay.
These gates control the flow of information
Okay.
over time,
Okay.
allowing the network to selectively remember or forget things.
So it's learning what to hold on to and what to let go of.
Exactly.
Yeah, and one popular gated architecture is the long short-term memory network, or LSTM for short.
LSTMs.
Yeah.
Okay.
Yeah, and they've been super successful
Wow.
in various tasks,
Right.
from natural language processing to machine translation, speech recognition.
It seems like for every challenge that we encounter with these neural networks, someone comes up with an ingenious solution.
That's the beauty of this field. It's constantly evolving.
That is really cool.
It is,
All
and
right.
it's not just about architectures,
Right.
but also training methodologies.
Okay, like what?
So there's curriculum learning, which is inspired by how humans learn.
Curriculum learning.
Yeah.
So we're making lesson plans for our neural networks now.
In a way, yes.
Okay.
So instead of giving it all the data at once,
Right.
you present it with a structured sequence of examples,
Okay.
starting with easier ones and gradually increasing the difficulty.
So it's like starting with the alphabet before you move on to Shakespeare.
Exactly.
Okay.
And this gradual increase in difficulty can help it learn more efficiently and achieve better performance.
Yeah, it makes sense. We wouldn't expect someone to run a marathon without training first.
Exactly.
So we need to guide our networks.
We do.
Okay.
Yeah.
So what other training methods are out there?
So there's transfer learning,
Transfer learning.
which is a really clever technique that leverages knowledge from previous training experiences.
Okay, so we're transferring knowledge from one network to another.
Exactly.
Wow.
Yeah. So instead of training a network from scratch every time,
Right.
you can take a network that's already been trained on a massive data set,
Okay.
maybe on a similar task, and fine-tune it
Okay.
for your specific needs.
That sounds very efficient.
It's particularly useful when you have limited data for your new task.
Oh, okay.
Yeah, so you're building upon that foundation.
So it's like taking an athlete who's already in top shape
Exactly.
and giving them some specialized training.
Exactly.
Wow. Okay, that's really interesting.
It is.
What else?
And then there's multitask learning.
Multitask learning. So we're asking our networks to become expert jugglers now.
You could say that.
So,
So multitask learning, you train a single network to do several related tasks simultaneously.
so wouldn't that be confusing for it and lead to bad performance?
It might seem that way, but the power lies in shared representations.
Okay.
So when it learns multiple related tasks,
Yeah.
it can extract features and patterns
Okay.
that are common to those tasks.
Okay.
And so this shared learning can actually improve its performance.
So it's like learning these transferable skills.
Exactly.
Okay.
That you can apply across different domains.
So it's a win-win.
Exactly.
Well, we've gone from these basic concepts
We have.
of forward propagation, back propagation, to these really advanced techniques
Yeah.
like curriculum learning, transfer learning, multitask learning. What else is out there?
Let's talk about generative adversarial networks, or GANs.
GANs.
Yeah.
I've heard of those.
Yeah.
They're all over the news these days. What makes them so special?
So they consist of two networks, a generator and a discriminator, and they're locked in this competition.
A competition.
Yeah. So the generator's job is to create fake data
Okay.
that looks as real as possible.
Okay.
And the discriminator's job is to distinguish between real and fake.
So it's like a counterfeiter trying to fool a detective.
Exactly.
Ah.
And through this back and forth, they both get better.
Okay.
The generator gets better at creating fakes, and the discriminator gets better at spotting them.
Okay.
And so they kind of push each other to improve.
This is amazing.
It is.
So what can they do?
Well, they've achieved incredible results in generating realistic images,
Yep.
videos, even music.
Wow.
Yeah, and the applications are endless. They're being used in everything from drug discovery to image editing to data augmentation.
It's mind-blowing
It is.
how these networks can generate such creative content.
They're transforming various industries.
Wow, this has been an incredible journey.
It has.
We've covered so much.
We have.
From the fundamentals to the cutting edge of AI.
Yeah.
A bit overwhelming,
It is.
but in a good way.
In a good way, yeah.
It's really given me a solid foundation. I want to learn even more.
Awesome.
And to all of our listeners, thank you so much for joining us on this exploration of neural networks.
Thanks for listening.
We hope you found it insightful and inspiring. And until next time, keep exploring, keep learning, and keep those neural networks firing.
Yep.